Hello and welcome back to another LeetCode video. We're looking at LeetCode 763 partition labels. It's one of the LeetCode 150 problems in the greedy category. And yeah, we're going to solve this today. So let's get started. Read the problem description. So we're given a string S and we want to partition the string into as many parts as possible so that each letter appears in at most one part. For example, the string ABABCC can be partitioned into ABAB and CC. But partitions such as ABA and BCC are invalid. That is because characters are spread across different partitions. Note that the partition is done so that after concatenating all the parts in order, the resulting string should be our original string S. And we should return a list of integers representing the size of these parts. And then here in the examples, we have a very long word of letters. And it can be partitioned into 3 parts of length 9, 7, and 8, which are the ones shown here. Now there's a second example where it can be partitioned into multiple parts, and that is because letter E appears in the very beginning and at the end, and the letter C appears at the very end and after, and at position 2 in the string. So that means it's impossible to create a partitioning that doesn't go over the entire range of the string. So, well, how do we solve this? Well, one way to do this would be to iterate over the string in linear time and remember the starting point when a letter first occurs and when a letter occurs for the last time. And then we suddenly have basically partitions where, well, intervals where we say, okay, we have to make a partition where like this maybe. And so we then have to determine, can we find non-overlapping partitions? And if we do so, we can make a cut after them and merge them. For example, here, partition A, that means the letter A occurs here and somewhere here. And that means A and C, they could be merged into one partition. However, since we have a letter B that appears in the middle of that partition, after it, we also need to merge them together so that we have a partition that contains all the letters A, B, and C, right? And we have partition C that starts somewhere here. Then that can become a second partition in our result list. We merge overlapping intervals. That would be one idea. That idea would take, well, we first have to convert the string into a list of partitions, and then we would have to sort these partitions by start and end index. And then we'd have to merge the partitions, and that would be, well, to determine them would be linear time, to merge them would be linear time, but to sort them would be n log n time. So we would have an n log n time algorithm and O of n space algorithm. That would work. However, there's a more efficient way to doing that. And the way to do it is to determine the partitions. Well, no, to determine the last index of a letter in the very beginning. And then as we iterate over the string, we're going to check, where is the last position of the letter A in the string? This case would be here. And we keep track of basically what is the largest, what is the window size of our current partition? We then run into letter B. Where does it occur? It occurs before the last A, so we're not going to change the size of our window, and so forth. And only when we reach the end of our window do we know that we have found a partition that doesn't have any letters that occur outside of it. So that is basically the idea that we're going to use. It's going to be O of n time and space. And we need to do a first pass to determine what the last index is of each letter. last index. And we're gonna make this a dictionary. Maybe a default dictionary. And then we iterate over all of the letters in S, right? For I in range length S, last index of the letter at position I is equal to I. So when we iterate over all of them, the last value written, the last occurrence index of that letter. Cool. Well, that's the preparation. Now, as a result, we need to return an array with the length of these partitions, right? That variable and return it. Now we're going to keep track of how large our current window is. And in the beginning it's 0, and we're going to keep track of the end of our window, the right side of the window. And that's also going to be 0. Now we just iterate over all of the characters again, like so. And we're going to take character at from a string S at position I. And at every step, we have to increase our window size. So when we're at position I equals 0, that means our window size is now 1, because we now have one letter in there. Now we use the trick that I've just explained to determine how large the window is going to be. Well, at minimum, it's going to be the current size, current end of the window, or the last index of the letter that we just encountered, right? Because inside a partition, all of the letters that occur in that position must be in that position. They cannot be outside of that partition. And we finally have to make a check that determines whether we've reached the actual end of the window. And that is the case when if I is at the end of the window, that means all of the characters in the window only occur in that window, and we don't have to extend the window anymore. In fact, we can say that we've now reached a partition end. And we only need to add the size of the window here, and then we initialize it for the next round with 0. And that is pretty much everything that we need. So let's run it through the test cases. There you go. And if we submit this, you can see that it also works. All right, so the greedy part of this algorithm is that we are immediately extending the size of our window using the information that we collected before, where's the last index of the current character. Run into a character inside a partition. We know that the partition must reach at least until the last occurrence of that character. So that's what this thing, right?